So this is going to be a video to help you through part 2 of chapter 14 from the exponentials and logarithms chapter in the year 1 textbook. This is a really important piece of information that you're going to learn, which we will continue to use throughout the rest of the year 12 maths, and it comes up a lot in year 13. This is a really big learning point. So we are going to be talking about the gradient graphs of exponential functions. We know what the graphs of exponential functions look like now, and we're going to talk about the gradient graphs. So far, all we've ever learned to draw and differentiate are polynomials. A polynomial is where we have an x to the power of some number. So x cubed is a polynomial, x to the power of 7 plus 3x squared take away 4x to the minus 2 is a polynomial, but x is the base. We know that for exponential functions, x is the power, and we have a base that's a constant. So 2 to the power of x is an exponential function. Minus 3 to the power of x is an exponential function. 7.2 to the power of x is an exponential function. And we don't have any idea what their gradient graphs look like, and we don't know how to differentiate them, which is a bit of a problem. We are going to learn today. Earlier in year 12, we learn how to draw the gradient graph of a function. So we went through drawing graphs themselves and then looking at what their gradient graph will look like. And we looked specifically, we did that by looking at where the stationary points were and what was happening to the gradient on each side of the stationary point. So for this one, this has a stationary point at 0, which means the gradient at 0 is 0, which tells us it's going to cross through the x-axis. It's going to cross through the origin. We then look at the left-hand side of that stationary point, because that's the only stationary point that this graph has. And from left to right, we need to think about what's happening to this gradient. This gradient is a positive value. And as we go towards the stationary point, the gradient of those tangent lines is getting smaller. So we've got a big positive gradient here, so big positive gradient, but getting smaller until we eventually get to 0. I'm just going to draw that in one curve like that. On the other side, what's happening to the gradients? The gradients are positive and getting bigger. So positive, so above the x-axis and getting bigger, will look like that. And we've got a fairly dodgy x cubed graph, or x squared shape, I should say. And we know from our differentiation that that's actually going to be the graph of 3x squared. But what about exponential functions? Can we do something similar for exponential functions? There's an exponential function. What happens if we try and draw the gradient graph? Well, there's no stationary points. Here, the gradient is positive. Here it's positive and a bit bigger. Here it's positive and a bit bigger again. Positive and a bit bigger again. So it starts off shallow, so small but positive. Small but positive. And by the time we get here, it's big and positive. And it's gradually increasing. So that would look something like this. But that's just another exponential function. So it would make sense to say that if you differentiate an exponential function, you get some other, let's use another letter, L, some other exponential function. That's pretty interesting. We can do better than that. We can come up with a rule for a very particular exponential function that we're going to keep coming back to over and over and over again for kind of from now on. And what I'm going to do is I'm going to use Desmos to help me learn a bit more about these exponential functions and their gradient graphs. So I've got a little Desmos expression or equation set up here, and at the moment it's set to 2 to the power of x. So this is the graph of 2 to the power of x. I've put a little slider in so that I can change change that base number to different values. And what I'm also going to do is get Desmos to draw me that gradient graph that we were talking about. So that's in green. That's the function itself. The red function is the function itself, and the green line, let me just show you the colours that I'm using. The green line is the differentiated version of the exponential function. And we've already seen that we get another exponential function. But look what happens now as I change A. The gradient function starts to catch up with the initial function. That gap's smaller than it was when A was, say, 1.5. What happens when I take A to like 4? Well, it's gone past it. It's increasing faster than the original function. When I take it back down to 2, it's not increasing as fast as the original function. Where's that crossover? Looks like it's roughly at 2.7. Can we do better than that? Let's try and zoom in. Okay, so we've zoomed in a little bit. Can we find 2.7, 2.8? So there's a number between 2.7 and 2.8 that allows us to match them up. Let's make these steps smaller. 2.701. Whoa, there it was. 2.718. Can we do even better? .718. We need to zoom in a bit more. Let's see how good we can get this. You might recognise this number already. Oh, I don't think it's going to let me go any. That's as good as I can get it, I think. Oh no. Here we go. Tiny, tiny increases. They look like they're close. Yeah, that's pretty good. So what number have we got there? We've got 2.71828. 2.71828. Let's write that number down. So we're saying that because they matched, when y is equal to 2.71828 ... whatever that number continues to be, when we differentiate that, we just get the same thing again. That's known as self-differentiating. You just get the same thing back. We've not seen that happen before. So this number here, this number must be pretty special. You might recognise that number. That number is what we give the letter E to. So you will hopefully have seen e to the power of x in your working whilst you've been at home. But this is why e is given this number. It's because it increases, its gradient increases at the same rate as itself. So they are, we talk about gradients being the rate of change. The rate of change of y is equal to the values of y themselves. So if e is just this 2.71828 number, then when y is equal to e to the power of x, dy by dx is equal to what? Well, dy by dx is just equal to e to the power of x. And that doesn't seem like a very big deal. That seems like, well, that's really easy. But that is really easy, but it's really, really important. That's going to go in a big box. That's going to go in your notes. That is going to be something that you need to remember for all the time that you are ever doing any maths. Okay? Just be careful that is a new rule. That rule is only when we see e to the power of x. It is not to be confused with the rule for differentiating polynomials. Differentiating polynomials has its own rule, and that is that you bring the power to the front and take one off the power. So when we see things written like this, then we use the polynomial differentiation rule. And when we see functions with an e to the power of an x, so when x is the power, we've got our own rule. Okay? Completely separate things. Don't muddle them up. I'm going to take that a little bit further. We are actually going to need to know how to differentiate multiples of x, and you will learn the reason why this is true, but at the moment I'm not going to explain why. I'm just going to tell you the rule. And the rule is that the k, it's the same thing again. So if I was to cover this up, you can see that e to the power of kx differentiates to e to the power of kx, but we times by k as well. Okay, so e to the power of kx goes to e to the power of kx times k. So if, for example, we had say, I don't know, y equals e to the power of 4x, then when we differentiate that function, we are going to get e to the power of 4x, but we are going to times by 4 as well. So let's just practice differentiate. That's my first example. Let's just practice a few of these using the rule that we've just learnt. Well, we've just said that this will be 4 times e to the power of 4x. What will happen when it's a negative multiplier for x? Absolutely nothing different. We're going to get the same function again. Still going to have e to the power of negative 0.5x, but we are going to times by negative 0.5 as well. So negative 0.5 e to the negative 0.5x. And for the third one, we've got 3 lots of e to the power of 2x, and that is going to be 3 lots of e to the power of 2x, but we're going to need to times by 2 as well. So that will become 6e to the 2x. So we just need to remember to times by this extra power value here, but not the x as well. That's a common mistake for people to write that e to the 2x would differentiate to 2x e to the 2x. That is absolutely not true. Not true. Okay, the x doesn't come down, just the number. we've kind of talked about sketching graphs already, so I'm not going to spend too much time on this, but this is about using your graph transformations. So how will y equals e to the 2x look compared to just regular e to the x? Now remember, e to the x is just 2.71828 to the power of x, so that's a normal exponential function. What will 2 to the power of x do? So that will be a sketch, scale factor a half, parallel to the x-axis. What will that look like? Have a think. You might want to sketch it first, and then I'm going to show you the answer. So let's use Desmos whilst I've got it open. So we've got regular e to the x, and then let's draw e to the 2x. What do you think? Oh, I need to zoom back out, don't I? Otherwise it's just going to look like a straight line. So the orange one is e to the x, and then we're going to draw e to the power of 2x. What do you think? Will it be above? Will it be below? It's stretching, remember? Stretching parallel to the x-axis, scale factor of a half. So it looks like that. It's the red one. So it's kind of below the orange line in this section, but then pops up and increases as x becomes bigger than 0. So that's those two. What's the next question? The next question is 10e to the minus x. So we need to think about what e to the minus x will look like first. And then we need to think about what 10e to the minus x will look like. So let's go from the very beginning. Let's think about e to the power of x, normal e to the power of x, which we've got again is our orange line. E to the power of minus x, what will that look like? That's going to be a really important graph for you to know. Hopefully you've worked that out. That's going to be a reflection in the x-axis. Okay, like we saw with the 2 to the power of x and the half to the power of x. It's a reflection in the y-axis because x has been replaced by minus x. And then we just need to go one step further and think about what that 10 is going to do. 10e to the power of negative x is going to be a stretch parallel to the y-axis this time, parallel to the y-axis. So we'll go much higher up in the y-intercept. Let me get rid of the orange one so we can see the two differently. Okay, this is going to be a value of 10 here now. So that's stretched in the y-axis, whereas the other one stretched in the x-axis. And then finally 3 plus 4e to the half x. Okay, there's a few transformations going on there. Let's start with the e to the x again. Think about what e to the half x will look like next. So let's get e to the x back. That's the red one now. E to the power of a half x is going to be a stretch, scale factor 2 in the x direction. So that's doing the opposite of what the 2x did. It stretched it kind of out left and right rather than squished it in left and right. What will happen if I now add the 4? Well, that's going to stretch in the y direction, scale factor 4. So that's going to stretch upwards and downwards. So it's going to come away from the x-axis if I add that 4 in. There you go. And then we had a plus 3 as well. That's a translation. 3 units up. So it shifted up. The asymptote, notice, look, the asymptote has moved. If I draw y equals 3, we can see the asymptote there. So those are that's the sketches for those 3 graphs. Obviously you wouldn't be asked all of those questions in one, but they will expect you to be able to cope with transformations to do with exponential functions. So it's just bringing the exponential work in with the transformations that we've seen in the past. This is a little bit mean, giving you 3 transformations in one. But we will need to learn about multiple transformations in Year 2 Maths anyway. Here's just each of those 3 graphs again. Okay, so that should be enough now for you to work through exercise 14b. So we've talked about what you get when you differentiate e to the x and e to the kx. We've talked about using our knowledge of graph transformations to help us sketch transformed exponential functions. And then next time we are going to start talking about logs. Logs are really, really important. And will come up a lot. That's probably where, if you've been looking through the work, that's probably where you've had most problems. So that'll be really good to kind of get onto. Okay, I'll see you soon.